Swayam Prabha. Digital India. Educated India.
A circle, break it down to two parts, rotate this guy about the z-axis, rotate this guy about the y-axis or x-axis, combine them together. U, C. This is with regard to as much as drawing can do. But there's a very interesting philosophy behind this. Okay, there are a bunch of C words. There are a bunch of C words that if you understand and if you think and analyze about those C words, okay, you will be great throughout your life, from now till the age you retire and beyond. This was what my last lecture was going to be about. It's still on if you guys are interested. I'll have to figure out a time. It's got nothing to do with the drawing that we are learning, but since this course is about thinking and analyzing, I thought it may be a nice idea for me to introduce to you those C words that you can cogitate upon. C word, cogitate upon. But that's for later, not now. Okay, I'll start by saying thank you. This is my penultimate lecture, 25th. Officially, my last lecture is on Thursday this week. So I'll start by saying thank you to all who have helped all of us in making us, you including me, think and analyze together. First, the tutors. First, the tutors. Professor Vinod Tare. So I'll start with civil engineering. Frankly, I'm not really sure how effective the slides have been on my webpage in making you guys learn. So a little feedback, whether effective, whether not effective, whether good, whether useful, whether not useful. Okay. There is a story. Back in 2003-2004, when you were still in grade school, Professor Vinod Tare, he was standing here and I was sitting over there as a tutor. And the idea that I should be using animations in trying to explain things to you actually came from him. So he used animations in his presentations. I was very, very impressed with, and I thought maybe I'll continue with that idea. He was a 5-star instructor. He's still a 5-star instructor. So I'm not really sure if I'll still be able to, compare myself with him, but the idea of using animations in slides, making you guys follow and teach, actually came from him. So he deserves another round of applause. Professor Punendu Bose. Tarun Gupta, Professor Tarun Gupta. Professor Rajiv Sinha. Professor Javed Malik. Ria George. From aeronautical, we have Bhardwaj. And we have Shantanu. From mechanical, we have Professor N. Kishore. Sitting right there. He's going to be teaching this course in the coming semester. And Professor Kishore, if I can see you, thank you very much. Your feedback was wonderful. And your idea about the three-point perspective was absolutely fantastic. So I enjoyed it. I learned it. Thank you. Professor Ashish Datta taught the course before. Professor Basantlal Sharma and Shakti Singh Gupta. I do not have the names of all the teaching assistants at this time, but they were there in the foreground, not here, but in the labs, and they were there for great help to you. So thank you to all the teaching assistants. And a person you have not seen, or you may not have seen. So he's a person who has been doing all this work in the background, preparing models, preparing AutoCAD stuff, and helping me with a lot of things. Ashwini Kumar. All right, so we'll start with a new topic, development of surfaces. I'm exhibiting a few solids here. Okay, some pyramid, well, 1, 2, 3, 4, 5, 6, hexagonal pyramid, which is truncated by a plane. Okay, another something very similar, a skewed pyramid here, a skewed tetrahedral here. Okay, this is a hexagonal pyramid again, regular hexagonal pyramid. This is a very nice structure, so which is again I think a hexagonal pyramid, but it has a cylindrical void and it has been truncated by a plane. Okay, another something very similar. So what I'll do is I'll pass these things on to you. You can take a careful look and return them back to me. Don't take it to your hostel rooms. But what is very interesting about all these solids is they have been made by paper, okay, and importantly, a single piece of paper. A single piece of paper. Okay. Now let me revert this question and ask you this: how would you want to prepare this so that you get the solid? How would you want to prepare that corresponding piece of paper so that you get this solid? And this is what this lecture is about. Yeah, pass it on. Don't keep the solid with you. Can you come from somewhere there? Anybody? Anybody? Do you know where Northwest is? Do you know where Northwest University is? Humanston. Anybody? All right. So here we go. Penultimate lecture. I was asking God as to whether he has or she has many examples on developments of solids, and I came across this nice setup, nice PDF from I guess IIT Guwahati, Aringdam Day is the name who taught this, and I liked a few pictures in this. Okay, and these are the pictures. So what you see is a box or a block, a cylinder, a tetrahedron, a cone, a sphere, and well, this is a tetrahedron. This is pretty much like a pyramid. Yeah. Okay, and what you also see is that they may have been made by paper. Okay, and how would you want to kind of unfold the paper so that you can lay it down flat on a plane? So perhaps you can cut one of the edges. You can make one cut over here. You can make one cut over here, another cut over here, open up and lay it down on a plane, and once you fold them back, you would get this cuboid, for example. Same thing with the cylinder. So cut this face apart, and make a cut along this direction, lay it down. So essentially the idea is that all of these solids, except for perhaps sphere, okay, they have been made by a single piece of paper. Okay, and the question again is, how would you want to prepare that piece of paper so that you can get the solids back? All right, so this is quite straightforward, right? The unfolding is quite straightforward. The unfolding over here is quite straightforward. So the method is the parallel line development, lay it open, cut and lay it open. Parallel line development, this is pretty much like a radial line development, pretty much like, for example, when you cut the pyramid, you open up, so to speak, a sector. Okay, not a rectangular piece of paper, but a sector. Same goes with the cone, and with the tetrahedron, you open up this piece of paper into triangles. Okay, so just an example. So example 1, 2, 3, 4, and 5, they happen to be examples where you prepare your piece of paper in such a way that you get the exact solid back. Yeah, this one is like an approximate example. We'll talk about that. Okay, so certain developments are exact, certain developments are approximate. So except for this example, all the other developments are exact. This one is approximate, and this one is, this point seems to be important. So for example, if you have a little void here on the surface, or maybe perhaps a void here, or a void here, or any feature, okay, when you are opening up that corresponding piece of paper, what do you expect? Should that feature be in should the feature be in true dimensions, or it should be in some sort of, untrue dimensions, so to speak, or projected dimensions? What do you expect? True dimensions? Everybody? This is what the intent is. So if you look at these surfaces, all features on these surfaces, they have to be in the true dimension, and that is the point that you have to keep in mind when you are developing a solid or developing a surface. Okay, true lengths or true shapes. All right, so this is an octagonal pyramid. Okay, let's try to lay it open on a plane. You have been given three views: the front view, the top view, the right view. Okay. Well, the question is to form an octagonal pyramid from a single piece of paper. So we have to figure out how to make cuts on that single piece of paper. Okay. Now look at this length, this horizontal length in green here. Okay, what's the corresponding projection? This guy here? Yeah? Yeah? Now what do you have to say about this length? Is this length in true dimensions? Why is that? Because the corresponding projection is parallel to the hinge in one of the views, right? So this projection is parallel to the hinge in one of the views, and therefore this one is in true length. So I'll call it TL1. Okay? Look at this projection over here in red. okay, and look at the corresponding projection in the top view. Is this projection in true length? Again, the same principle. So this projection here is parallel to the hinge line in this view, and therefore this one should be in true length. So I'll call it TL2. The entire thing that you have to keep in mind is to figure out or keep figuring out the true lengths. Okay? Is this information good enough for you to work with a paper on a plane? Is it information good enough for you to transfer the entire information that this surface has, this solid has, on a single piece of paper? Yes? All right, let's see. So you have this true length, TL1, all right. Taking one of the ends of TL1 as the center and the radius as TL1, draw an arc, okay. And taking TL2 as dimensions with this vertex as center, draw, in fact, cut the previous arc with a new arc. And keep cutting these arcs. How many times are you going to be cutting? Huh? 8 or 9? Keep cutting. And all these lengths, they are going to be what? All these lengths, they are going to be what? TL2. Okay? So there have to be how many cuts? So 1, 2, 3, 4, 5, 6, 7, 8, corresponding to the number of vertices that you see in the top view there. Yeah? And of course, join these points with the center. So what you have is something very simple. So if you make this sector out of a paper and fold it at these, so to speak, lines, okay, you'll get this solid back. Right? Right? Pretty simple. Let's make our lives a little more complicated. What if the pyramid is truncated? What if I have a plane that is cutting the pyramid? Okay? Then what? The base will be the same, so we'll have to be working with this entire picture over here. Just that we have to be a little worried about the intersection points between the octagonal pyramid and this plane. Yeah? So let's try to figure the intersection points first. Okay? You need to know where the intersection points are. Where are they going to be lying? Where are the intersection points going to be lying? Well, I mean, you have these edges, right? So the intersection points, they have to be lying on a plane, this plane, and they also have to be lying on these corresponding edges. All you need to do is like project those intersection points in the top view and the right side view. No? All right, so keep projecting. So this one lies on edge number 6. Okay, this one lies on edge number 5 and 7. I don't know, 5 perhaps. So keep projecting. Okay, and you essentially will be figuring out these intersection points in the top view. Okay, all except for 2 of them. Those intersection points which will be lying on the vertical edge over here, number 4, and the edge behind it, number 8. So 4 is behind. So number 8, which is facing you, and number 4, which is behind this. How do you figure those points of intersection? You can make this projection, perhaps. Okay? So if you can make this projection, this is number 8, this is number 4. You'll be getting the corresponding intersection point over here and over here. Project them backwards and onto the top view and get those intersection points. Okay? Or otherwise, Or otherwise, if you want to be a little more tedious, maybe make any measurement, make the hinge line, make the same measurement over there, make the hinge line, you know, and something that you have learnt in your lines and planes thing. Okay. So measure that distance, transfer that distance over here, and measure this distance, transfer this distance over there. So these are your two intersection points. And the second, of course, was quite right. So you can directly project those intersection points from the profile view and transfer them onto the front view. So these are your intersection points. I'm not labeling them. So labeling is something that you'll have to do later. And join those intersection points to get this contour. Okay. Now, when I say that the pyramid is truncated, I essentially mean that this part of this pyramid is taken off and it's replaced by a plane covering the top portion of the pyramid. Okay. So this is the top lid of this pyramid. What's the bottom lid? What's the bottom lid? The octagonal face, no? 1, 2, 3, 4, 5, 6, 7, 8, the octagonal face. All right. Okay, so you can as well project these intersection points onto the profile view. Okay, get them on the respective edges of the octagonal pyramid and complete the contour. Right? Is this contour in true shape? Is this contour in true shape? What did I say? So if you have to transfer everything in such a way that you have to lay down those features on a plane, you have to get the corresponding things in the true shape, no? Well, so this is the actual truncated pyramid that you see. The actual truncated pyramid that you would see. The top portion of the pyramid is gone. Okay, this is the top lid of the pyramid which is covered, so the pyramid is not open, and of course the bottom face of the pyramid is covered by that octagonal face. All right. Always label the points. So I made a mistake of not labeling the points, but you should be always labeling these intersection points. Every point that you're working with in your intersection and development exercise, always label them. Okay, so now I am labeling those points. A, B, C, D, E. Correspondingly, A over here, there are two B's. A, B, C, D, E would go, you know, from here to here. A, B, C, D, E would come from here to here. All right, so always label your intersection points. All right, so I'm done pretty much. Now I need to get this contour in true shape. Okay. Well, yeah, so something that I already told you, it always has to be the true lengths and true shapes that need to be transferred onto the piece of paper. Okay, and we need to find them as a part of the exercise and development. All right. Now, let's worry about this lid later. Let's worry about this lid later. Let's worry about the rest of the edges. Look at this edge. This edge would lie on which edge of the octagonal pyramid? 6 or 2? 6 or 2. What's the corresponding projection? What's the corresponding projection in the front view? This one? Okay, so this is edge number 2. Is this in true length? Okay, so if this is in true length, it should be possible for you to transfer that length over here. There. Is there any 2 that you're seeing here? No? That's fine. How about this entire thing? This is on which edge? Number 6. The corresponding projection? The corresponding projection here is this in true length. You need to transfer that onto edge number 6 there. Okay? So the intersection point over here would be A and the intersection point over here would be E. Always label. Yeah? All right. Let's look at this edge. Okay? Intersection point C. All right, so where is it? Can you identify the corresponding projection in the profile view? C would be on 8. And it would also be on 4. So 4 and 8. 4 and 8. Yeah? Is this in true length? All right, so it should be on 8. Is this also in true length? Great, so it should be on 4. Wonderful. How about the lengths on edges number 1, 7, 5 and 3? Lengths on edges number 1, 7, 5 and 3. So 5, 7 are here. 1, 3 are here. So if you're looking at the corresponding edge over here and its projection there, okay, so this is slant and so is this. So is it possible for you to extract the true dimensions directly from these two or from the information given? Huh? It is possible. No algebra, no fractions, just geometry. No root 2, root 3, root 4, root 5. No pi, just geometry.
So we can project it on, we can project B onto the.
Yeah, I'll come in. I'll come there. I'll come there. All right. So these are intersection points C. Okay. All right. What about the rest? We are trying to address that. Okay, so look at this projection and try to figure the corresponding projection in the top view. Okay, B7. B7 is this one. B5 is this one. Yeah? I'll do a little trick. So what I'll do is I'll displace the line in both views. I'll displace the line in both views. Okay, I'll displace the line in such a way that one of the vertices of this line, the true line, lies on vertex number 6. You follow that? You follow that? Just rigid body displacement. I have kept the lengths of these corresponding projections the same, just rigid body displacement. And just in case if you remember the method of rotation to figure out the true length, precisely if you do that, if you rotate this, then what will happen to this projection? You take a projection from this point here down, okay? This height would remain the same, and eventually this guy would come here. Just using the method of rotation. Yeah? So what you have done, so let me go back. So you have identified these projections, made rigid body displacement, shifted the line, okay, such that one of the vertices of the line lies on number 6, edge number 6. Followed the method of rotation. Okay, when you do that, this guy gets rotated to lie on the slant surface. Yeah? Now you have the true length. You have the true length for what? This guy here, B7 and B5 as well. Yeah? Take that true length and perhaps transfer it there. Okay, likewise, I can do the same thing for this. Identify this projection, the corresponding projection is 1D, and on top it's 3D, not 3 dimensions but 3D. Okay, shift, follow the method of rotation. This guy gets rotated to lie on this slant edge. Yeah? Yeah? This is just for this is just for you to understand. One method that I'm going to be talking about now is going to be much simpler. So what you realize is whatever length you have here, if you just project them in such a way that they all happen to be on the slant edge of this pyramid, essentially you're going to be getting the true lengths over here. Okay, this is where I'm coming to. Realize that to get the true lengths, you need to project the intersection points onto the extreme right or left edge of this solid. Yeah? So this point is lying on this edge. This point projected over here. From here to here, you'll get the true length. This point, again, projected onto the extreme left, get the true length. Likewise for D, and point E is already there. Right? So if you project all these intersection points so that they lie either on this edge or this edge, the corresponding lengths, they'll all be in true length. That's a much simpler method. So these are the corresponding projections, either on the left or on the right. So once you have these projections, okay, transfer them onto that piece of paper, draw the radii or draw the arcs if you want to. You don't have to, but if you want to, draw complete arcs. But what is of interest to us are these edges, edge number 1, number 7, number 5 and number 3. This is where we want the true lengths to be. Yeah? Alright, so let's work with edge number 1. This length is what? This length is this point getting projected over here, so it's this length, right? It's on edge number 1. So one here and the other one here. And so is the case with edge number 3 also. Yeah? So this is 1 and this is 3. Okay? So 3 of these lengths, they get transferred. How about number 5 and number 7? Be projected over here. So it's this point here now. Alright, so of course label, and this is the true length on edge number 5 and this is true length on edge number 7, same. Are you with me? All of you? By the way, my teacup, how many of you think that this is actually a torus? A torus. Torus. This is actually a torus. Is that true or not? Have you ever played ring? That ring is a torus. Do you remember playing ring when you were kids or even now? That's a torus. So this cup is actually that ring. Do you believe me? Do you believe me? Huh? You don't believe me? Louder. Do you believe me? All right. But that's true. This is actually a torus. Anyhow. You know, there's something called topology. Topology, science of connectivity or discipline of connectivity. So you learn things about connectivity, theory about connectivity in there. So many of the guys in electrical computer science, they'll be learning about networking. Network, that's connectivity in a way. So, you know, in your third year, in your fourth year, when you learn about topology, when you learn about homeomorphism, that is where you'll actually figure that this is a torus. Okay, but that's too late for you. Not this time. At this time, it's engineering drawing. So, all right. So once you have transferred all those true lengths on the respective edges and labeled the intersection points properly, okay. All right. So I'll make a little change. So what I'll do is I'll change the color. I'll change the color of these lines, and also will I change the representation of these lines. Instead of denoting these lines as solid lines, I'm denoting them using hinge lines. Why? Why? Because those are the locations where I am creating folds. Okay? Those are the locations where I'm creating folds to get this solid back. Right? To represent that the paper is bent or folded at these edges. And then, of course, close the contours. So if you take a piece of paper, okay, cut it in this fashion, fold it at the respective locations that are denoted over there, you'll get that solid back. With the difference, the bottom plane and the top lid, they will not be there. So it's going to be an open, truncated pyramid. Okay, let's work on that. Again, so you're going to be working with graphite pencils, so your drawing is going to be gray, not colorful. To get the top lid, once again, if I may remind you that you have to get true features and transfer them onto the paper plane. Right? So you need to determine the true shape of plane A, B, C, D, E, D, C, B, A. So this plane right here. Do you know how to get the true shape of a plane? Huh? Do you see the edge view of this plane? Do you see the edge view of this plane? Which view is it in? Which view is it in? Front view, all right. Draw a hinge line. Shoot projectors perpendicular to that hinge line. Transfer distances. Transfer distances. You know that, so I'm not going to be going through it once again. Okay. Transfer distances, and then get the true shape of that top lid. Okay. All right. So where is this lid going to be? Of course, you have to label these points also. So where is this lid going to be? Somewhere over here or somewhere over there? Where is this lid going to be? Huh? Well, it's going to be somewhere over here, no? Yeah? Let's worry about that in a while. All right, so by convention, this is what we do. We start developing the surface in such a way that we start with the shortest edge on the surface. So if you look at these edges, and if you figure out the lengths of these edges, you will find that this would be the shortest in length, and you start with that. So the edge you start with, you have to end with the same edge, because you have to glue the corresponding edges. Yeah? So this is what I have done. So instead of starting with edge number 1, I figured that edge number 2 was the smallest, 2E was the smallest. So I started and ended with edge number 2E. Okay? Conventionally, start development with the smallest edge and end with the same. All right, so rest of the information is taken away. What is important is the lateral surface of the solid, the top lid of the solid, and the bottom face of the solid. Okay? This one constitutes the lateral bounding surface of the solid, constitutes the top bounding surface of the top lid, the bottom face. Okay? That's of course in true shape. What you need to do is rotate these guys, okay, and align them appropriately onto the main developed thing. So notice where I am aligning this face over here. So notice AB, and looks like I am aligning the two ABs together. Right? Likewise, rotate the top face and align the corresponding edges appropriately. So I align one edge together. So I align this guy with this guy. Right? Now that's a single cut that you need to make to get the entire solid back. Yeah? A single cut you need to make on a piece of paper to get the entire solid back. This is what development is. If you cut this paper, fold it and glue appropriately, you will get the bounded truncated pyramid back. Is the location of these two planes important? Are the locations of these two lids important? These two faces important? Can you locate them anywhere? Theoretically, can you locate them anywhere? Would the location of the top and bottom bounding surface make any difference? So for example, if I choose to locate the bottom face there and the top face here, should be okay. Should be okay. Yeah? Do not forget to introduce the seams. Those are little extra things that you would want to provide over here, so that when you fold the solid back, or when you fold the solid, you should be able to provide enough paper to be able to glue the solid back. Now, like, so these are the seams. Right? So if you fold this thing over here, if you fold this thing back, you know, so you're going to be gluing at these little pieces of paper over here and over here. Now figure what the problem is. Figure what the problem is. So if you allow for a little extension at this location, this is interfering with this laterally developed surface. Yeah? This location here. So you got to leave sufficient gap or space for the seams. So something that you'll probably want to keep in mind. Yeah? Oh, you want to say that this is to be represented by? Well, technically, all right. So if I may repeat, what's the name? Shubham. So what Shubham is asking is whether this line is to be represented using the hinge line convention. With the same logic that, well, we are also folding, we are also making a fold here. All right, any other question? Were you with me throughout? Were you with me throughout? Were you with me throughout, out of the blue? Yeah? All right. Can I have my solids back? Can I have my solids back, please? Yeah? Shouldn't there be a 2E here? There should be. True truncated top view. Yeah? So do you agree, wait, do you agree that the important thing for us is to show the true shape of the open lid, of the top lid? It doesn't really matter how you get it, so long as you get it. Any other question? Okay.